Okay, so let's build the last step of our cleaning process for these paths. So from last time, I'm just going to copy paste this one more time, and I'm actually going to copy paste another area from here. So let's copy paste that, and actually put that at the top here. So every iteration of this loop, first we're going to remove the short ends. We need to make sure that we don't set this threshold too high. And let's set the feedback to 1 first. Okay. So what we're doing is first remove all the short end pieces. And after that, we want to collapse all the other areas, the other edges. But if we do that, we actually don't see any results, because right now, okay, that should actually maybe just an area that's slightly too large, which in general you don't see a lot of stuff happening. So that may be because we actually want to do another polypath here, just to make sure that it's clean. Yeah, because stuff like this, we want to actually have one single edge. There we go. And then we measure again the new primitive that we generate for every primitive. So now it might actually start to remove some stuff. No, not a lot. Let me double check this. Yeah, that seems about right. Oh wait, of course, I wasn't back on the edge collapse yet. So yeah, and without the polypath, it still does some work. But if we re-enable the polypath, it actually cleans up more. So we need to make sure that we remove the group and again do a polypath to clean again. And then remove all the edges in between for the next iteration. So what we can do now is actually increase the amount of iterations that we do. And if we set to 10, we probably will get a very simple network. Oh, wait, yes. Yeah, so we get rid of a lot of stuff. I'm just going to add a no here, just to be able to set a template flag and then see what we remove. Okay, so what we're actually going to do is reduce the sensitivity here, because if we run this loop 10 times, the size of the collapsible area will become larger every time. So we can start off a bit smaller. Yeah, now we start to keep a lot more. Now we actually have a nice way to control how aggressive the filtering is. In a personal setup, I use 2.5, but we might be able to go a bit higher than that. Let's say 4. Okay. Okay. And something, yeah, we want to do in post again, just in case, yeah, we generate stuff like this. And we actually want to get rid of those things again. So I can just copy paste that. Actually, only this one. I'm just going to say remove this pieces, and in this case, I'm actually going to say if the end is 1 on one end and on the other one, then I'm going to remove, and I'm not even going to check the length of the edge. So you can just delete all spare parameters to get rid of that, and I should get rid of that. So it will just remove all the primitives that have 2 points, both with no other points connected to it. Okay. So let's create another wrangle to detect all the new end pieces, endpoints. So stuff like this. And we can just type this one again because it's relatively simple. So group endpoints equals neighbor count of the current point number equals 1. Okay. Group endpoints. And now I'm actually going to do a small trick to remove, also let's get rid of the templating, get rid of some of the double paths, let's say. So for every island or for every endpoint, I only really care about the shortest path. So we will use the find shortest path node for this. And I'm going to say from each start to each end, I'm just going to say endpoints. Okay, so right now it removed a lot of stuff, and that is because here there's not an endpoint, but basically a roundabout. So what we probably want to do is, before we start this cleaning process, actually start actually grouping these ends together first. Larger again. So I'm just going to copy paste this node at the top. I'm going to say fuse, set it to snap, and only do endpoints. We can set this radius quite large. and then we can simply do another fuse to consolidate, and again do a polypath. Okay, so that should simplify the paths a little bit, although it actually generates even less ends. Okay, these are paths that start to look like stuff that we want, except we probably want to keep a little bit more than what we have. Quickly check. Okay, yeah, I think that's why I set the tolerance a bit lower in my example file. Yeah, okay. So yeah, now you can start to see how it starts to work. Yeah, and again, basically we get to 2.5 to have a nice result like I had in my example file. Okay, so right now, yeah, we need to do some more cleaning. This is simple cleaning, luckily. So let's first do a fuse. And what we could do now is use a polypath, but this is something we'll have to do later. So right now it will just clean the path. But something we first want to do is actually control the total amount of paths. So we can just use a delete node for this. And we can say delete by range. And say out of 100 points or primitives, we want to keep this many. But yeah, what we probably want to do is add a sort node and sort by randomness. Sort them in a random order. And now we can start to choose how many paths he wants. And now you can see that the randomness actually controls which paths we will keep in the end. Okay. So yes, that leaves just these kind of pieces. And we will again remove these. Actually, I want to, in this case, group it by points. So I'm just going to say group intersection. You can also do this in a group wrangle. It doesn't really matter too much. Name counts. Bigger than 2. Ah, yes. Okay, that's why. Okay, so basically what I'm doing is grouping all the intersections. And now I want to do a group command. from points to primitives, group the intersections, and now you can see that this is not grouped. So basically only keep primitives that have intersections in them. Yeah, and then we want to remove everything that's in this group, but not too long, because we probably do want to keep this path, but maybe not this one. Okay. And in this case, instead of using a measure sub, actually going to do something else. Actually going to measure the primitive inside this wrangle. You can use the primitive intrinsic function for this, and the one we need for the perimeter is measured perimeter. Of the current primitive number. And also, just to make sure that if you forget this exact name, you can find it here. So if you go to primitives, you can go to intrinsics. Oh, sorry. Wait, was this changed in 16.5? Oh, wait, there we go. Okay. No. Interesting. Ah, okay. Yes. So these are the detail intrinsics. So stuff like the point count and the groups that exist in geometry. And here, I would have expected to see that. But yeah, maybe it's a bug of this version. Or maybe it's because, oh, there's no primitives, that's why. I think. Yeah, there we go. So yes, so you can have bounds closed to check if the primitive is open or closed. Measured area, perimeter, there we go. Okay. So measured area. And we want to actually use the opposite of this group. So everything that's not in this group, we want to delete, but only if the perimeter is smaller than a certain value. So if min length we remove the perimeter and also the points on the perimeter. Okay, so let's specify a primitive length. Okay, so yeah, at 250 we do remove this one, but we keep this one. So if I would go much higher, we remove both, but I only want to remove this one. Okay. So what we have now are just the guide curves. We still need to actually make nicer flowing curves. So let's do that. So this is where we use the polypath to clean up the results. And now I'm going to, yes, again remove all the points in the middle. So we only have the most bare bones of paths. I'm going to use another fuse sub. I'm going to set it to unique. So what that does is that it will split all the points at the ends of primitives, or if you're using quads or triangles, it will split the points where it would have connected to another primitive or triangle. And that is important because what we're going to do is we're going to create a path from every point to every point using the find shortest path. And we're going to use the from each start to corresponding end. But this node has a quirk that it requires the same amount of start point as endpoints, which is kind of logical. But if you have duplicate points in start or end points, it will not count them. So it will print a warning that you don't have the matching number. So if we make sure that every point is a unique point, we can't have double points in this list, so we won't have that problem. Okay, so what I'm going to do is actually go up quite a bit in the network. I think here. Yes, okay, so here we have our network before we start cleaning it, and we will actually use this to guide our paths. I'm just holding Alt and clicking to generate these dots. And now we need to actually generate that group. Second. There we go. Yeah. So actually what we can do is just copy paste from one of these. Yeah, from node 2, I guess. We just use that. We're going to create a points group. And actually we want to run this over primitives. Path starts is going to be points 0. And set point node group path ends is going to be points 1. Okay. I think I forgot a bracket or something. Ah, yes, of course. We need to set the group to 1. Okay. So now we should have 35 start ends and 35 path starts. And we can specify them in there. And now we should start to see some nicer paths. Okay. Not yet. As you can see, it doesn't seem to actually connect the right endpoint to the right start point. And that is because the point numbers here do not match at all the primitive numbers, the vertex ordering. So to solve that, we can simply use a sort node. And before we actually group our points, we can use the sort by vertex order. So now we actually start to see like the second point of a primitive is always the next vertex number. I can show you like this. If you go to the vertex tab, before the sorting, this number is not related to this one at all. But after the sort, you can see that it's like a clear progression. So after that, it should actually generate nice paths. So we go from this to this, and now we can actually start to increase add some extra features, let's say, to the pathfinding. In our case, I'll just add one for now. I'm going to add a turning attribute. I'm going to set it to 1. And in the find shortest path node, we go to path costs. And we will say consider turning costs, which will increase the length, the amount of time that it will take to compute quite considerably. Ah, yes, okay. I need to enable this. And now this field becomes available to type turning. And now we should start to see a slightly different path. Yes, okay. So basically, increasing the value of this attribute might decrease the amount of zigzagging. So basically, a curve that doesn't turn at every grid point is actually cheaper than one that zigzags all the time. Okay, so let's add one final smooth. And we don't want to overdo it. I think just the defaults are probably fine. And go a bit higher. The curve resolution is high enough that we can actually maintain our shape while having a high smooth strength. Okay, so now we just need to save. So I'm just going to go all the way up top here, Control C, Control V, and I will name this cache walking paths. Okay. Now this save to disk. There we go. So now we have our new paths in our cache. Okay. So in the next part of the tutorial, we're going to use these paths to affect again the terrain, and we'll add some extra detailing on the terrain, some propsing to actually reuse the biomes that we generated in the first set of this tutorial series. And yeah, generate some trees and rocks and stuff. Okay, see you there.